Hi everyone, welcome to KULTREP. So in this session, let us discuss about the DC to DC converters. So I will start the power electronics also parallelly. So in a power electronics, I will take the first topic as DC to DC converters, and then converters followed by the inverters and followed by the power semiconductor devices and drives, right? So let us complete the syllabus in that manner. So now let us start our session, which is DC to DC converter. So in this DC to DC converter, let me start with the very basic fundamentals. So for example, what is DC we'll start from what is DC to DC converter. So for example, what is DC to DC converter? So a DC to DC converter which converts fixed input DC into the variable output DC. So here the output voltage is a function of the duty cycle. So now, what is DC to DC converter? The input voltage is fixed. Let us assume that it is a VDC. So if I connect the load here, the output voltage is variable. I can get the variable output voltage. So how could I get the variable output voltage? So here the elements of the DC to DC converter are switch, inductance and the capacitor. So the DC to DC converter circuit consists of a switch, inductor and the capacitor. So and it is a function of the duty cycle. It is a function of duty cycle. So let us see what is duty cycle and everything in this session. So now what is the definition here? A DC to DC converter which converts the fixed input DC voltage into the variable output DC voltage. So here the output voltage is function of a duty cycle. Right? So now let us see one by one. Let us see one by one. So here let us take a basic DC to DC converter. So without the power electronic switches and inductance and capacitor. So for example, I took this circuit which is a series R circuit. So two resistors are there. So here RS, let me call this as a RS and let me call this as a RL. Two resistors are there and they are connected in series. So if I apply the VDC, so if I apply the VDC here, right? If I apply the VDC here, so let me assume this as a V0, output voltage. So and the current flowing this as IS and current flowing through the load is I0. So both are same because it is a series resistive circuit. So assume that this resistance is a variable resistance. Now, if I find the output voltage by applying the voltage division rule, so V0 equal to, so here V0 equal to Vs into or VDC into RL divided by RS plus RL. Here RS is the variable resistance. So if I vary the RS, the denominator varies, and if it is varies, V0 also varies. But there is a disadvantage in the circuit. So what is that? If I find the efficiency, that is output power by input power. So what is output power here? I0 square into RL. So what is the input power here? So I0 square into RS plus RL. So I0 and I0 square will get cancelled and RL efficiency equal to RL divided by RS plus RL. And this RS is variable. For example, if I increase the RS to get the required output voltage, so what will be the efficiency? Efficiency reduces. But it will operate in the poor efficiency, and here it is a resistive load, here it is a resistance, so it dissipates some voltage across here, which is equal to IS into RS. So there is a disadvantage in the circuit. So what we have to do, and this resistance should be replaced. By which element it has to be replaced? So the element should have the property of average power across that element equal to 0. Which is that element? For example, if I replace this resistance with the switch, what is the characteristics of switch? The average voltage across the switch, which is not equal to 0. The average current flowing through the switch, which is not equal to 0. But if you find the the average power across the switch, which is equal to 0. So that means if the power loss across the switch equal to 0, the input power equal to output power in this case. So the input power equal to output power, I can get the efficiency as 100%. I can get the efficiency as 100%. But by using the switch, how can we get the variable output voltage? Let us see. For example, I replace the resistance with the switch. I replace the resistance with the switch. So let us assume that, so it is a input voltage is VDC and output voltage is V0, and the polarity will be assumed like this. So let it be the I0. So now let us calculate the output voltage of this circuit. So let us see how the output voltage can be varied by varying the switch on and off, right? So now let me draw the V0 here. So let us assume that it is operating for the period of T, that is total time of the switch. So and T on is the on time of the switch. T on is on time of switch. T on is on time of switch. So now let us assume that from 0 to T on, the switch is in on condition. If in the 0 to T on, if the switch is in on condition, so what is the output voltage? The input voltage is directly applied across output voltage. So the output voltage is VDC. So after T on, let us assuming that this period will be the off time. So during the off time of switch, so what is the output voltage? So the current flowing through the switch equal to, get the current flowing through the load equal to 0, so that the output voltage is equal to 0. So that the output voltage is equal to 0. So 0 to T on, it is VDC. So T on to T, it is equal to 0. If I find the average voltage, so it is a cycle, it repeats, right? So if I find the average voltage, so how could I find the average voltage? For example, if I want to find the average output voltage for this waveform, so what is the average output voltage? So the average output voltage V0 equal to VDC into T on, the area of the V0 waveform, so which is equal to VDC into T on divided by total time period. Let us take one cycle which is equal to total time period. So which is equal to VDC into duty cycle. So duty cycle D. So now what is the duty cycle? So duty cycle equal to T on by T. T on by T. So now if I vary the T on, so how much it will be changeable? How it will be changed? So if I vary the T on, so the output voltage will also varies. The output voltage will also varies. So here D equal to T on by T. So how much the duty cycle, what is the range of the duty cycle, how much duration we can vary? So let us understand. So how much duration we can vary the T on? So from here 0 to T on. For example, let this instant is T on 2. So let this instant is T on 3. So let this instant is T. So what is the maximum duration we can vary the on time of the switch? So which is equal to total time period of the switch. So now, so if it is T, what is this value? If T on equal T, duty cycle equal to 1. If T on equal to T, duty cycle equal to 1. So what is the range of the duty cycle? The range of the duty cycle we can vary in between the 0 to 1. Right? So be clear here itself, so that you can't have the doubts or confusions in the overall DC to DC converters, right? So understand here itself, clear all your doubts. So the duty cycle is T on by T, and the duty cycle is varying in between the 0 to 1. Now, so here we have replaced with the switch, right? So is there any other elements are needed? Definitely needed. Why? Because, so here the output voltage is not pure DC waveform. So it is a pulsating wave. So for this we have the voltage harmonics If I draw the current waveform, so which is equal to IDC by R, which is also pulsating, so it has the current harmonics also. So in the source, it is injecting harmonic currents. So in the output voltage, it has the voltage harmonics. To eliminate the output voltage harmonics, we should include the capacitance in the circuit. To eliminate the input current harmonics, remember this point. To eliminate the input current harmonics, we should include the inductor, right? So now, let us see how we can find the harmonics for this waveform. So how can we find the harmonics in the waveform? By applying the Fourier series analysis. So how can we apply the Fourier series analysis? So if you apply the Fourier series analysis, I am writing the expression directly. So V naught equal to VDC into T, VDC into T on by T, which is equal to duty cycle, VDC into duty cycle plus sigma n equal to 1, 2, 3 and so on, which is the order of the harmonic, so which is equal to 2 VDC by n pi into sine n d pi, sine n d pi minus cos n omega t minus d pi. So which is the Fourier series expression for this waveform. So now, if I want to eliminate the one particular harmonic, what will be the duty cycle? So what is that? Listen carefully. For example, my load doesn't require fifth harmonic. So for example, it is more affecting the load if it is fifth harmonic. So I want to eliminate the fifth harmonic. So now, to eliminate the fifth harmonic, I should operate this DC to DC converter in a particular duty cycle. What is the duty cycle? So let us take one example. So now, let us understand clearly. For example, so I want to eliminate the nth harmonic. So where n is the order of harmonic. N is order of harmonic. Order of harmonic. So if I want to make nth harmonic equals 0, so if I can make this term as 0, so the harmonic will be equal to 0. The particular harmonic will be 0. So which is equal to sine nd pi should be equal to 0. So sine nd pi equal to 0. So how can we find that? Sine nd pi equal to 0. So which is equal to, so for all pi instants, the sine will term which is equal to 0. So which is equal to sine into k into pi. What does it mean? So the sine waveform will be 0 at pi, 2 pi, 3 pi, 4 pi. Like in all the terms, when k equal to 1, 2, 3 and so on, the sine wave equal to 0. So from this n into d into pi equal to 0, which is equal to k into pi. So where pi and pi will get cancelled out, so duty cycle equal to k by n. Where k equal to 1, 2, 3 and so on. So where n is the order of the harmonic. What is the duty cycle? So to eliminate the nth harmonic, that is particular harmonic, the duty cycle should be equal to k by n. So let us see one example here so that you can understand clearly. Don't get any doubt here, just clarify every doubt of you. So right. So now, for example, let us take one question here. In a DC to DC converter, so if you want to eliminate fifth harmonic, what is the duty cycle? So to eliminate the fifth harmonic, so what is the duty cycle here? So D equal to K by N is the formula. Now, which harmonic we are eliminating? Fifth harmonic. So that is N equal to 5. So if I substitute n equal to 5, so what is this one? K by 5. So which is equal to 0.2 into K. Duty cycle equal to 0.2 into K. So I will substitute the K value. K equal to 1. So what is the duty cycle now? 0.2. K equal to 2. So what is the duty cycle? 0.4. So K equal to 3. When K equal to 3, so what is the duty cycle? 0.6. So when K equal to 4, what is the duty cycle? 0.8. So when K equal to 5, what is the duty cycle? 1. Right? So can we increase further? No, because the duty cycle range is 0 to 1. So if I apply if I apply for this formula, so D equal to K by N, for all these duty cycles, if I operate the DC to DC converter for the duty cycle 0.2, either of any duty cycle 0.2, 0.4, 0.6, 0.81, for all the duty cycles, so what is the thing is here, the fifth harmonic will be eliminated. Fifth harmonic will be eliminated. So this is how we can eliminate the order of the harmonic, particular order of the harmonic. Select two harmonic elimination. We can eliminate the one harmonic. Now let us see. So now let us see design of the DC to DC converter. So now let us see the design of the DC to DC converter. So what is the design of DC to DC converter? Let us see. So here, let me take one example. How the DC to DC converter can be derived. So as we know that we have the buck converter, boost converter and buck boost converter based on the voltage levels. So now let us derive the buck converter topology, boost converter topology and buck boost converter topology. For that, let us learn the basics from the very fundamental level. Let us learn the DC to DC converters. So for example, so we have the series element here. We have the series element here. So let me call this as a series element, not the RSC, series element. Series element. Right? We have the series element. So let us assume that it is a DC to DC converter. The input voltage, let me assume this as 100 volts. For example, it is 100 volts. So let us assume that it is operating as a step down converter. So that means output voltage is less than the input voltage. Let us assume this as a 50 volts. Right? 100 volts and 50 volts. So let us assume that the current flowing through the element is 10 amperes. So to get the output voltage 50 volts, so what is the condition? So the series element should dissipate some voltage across the series element, so which is equal to how much it should be displayed. So 50 volts it should be displayed, so that in the load it has the 50 volts. 50 volts plus 50 volts is 100 volts. So this is the case, right? Now, so if I use the series element here, only series element here. So if I find the output power, so what will be the output power? So input power equal to 100 into 10. So which is equal to 1000 watts. So if I find the output power, which is equal to 50 into 10. So what is the efficiency? Which is equal to 50%. If I consider the practical case, even if I kept the switch here, only switch here, so what happens? Because of the series element, some power will dissipate here. The topology should consist of shunt element also. So which is equal to shunt element. What is this purpose of shunt element? To get the efficiency as 100%. What should be the current flowing through the load? So it should be 20 amperes. Then it will be 100 into 10, which is 1000 watts. 50 into 20, which is 1000 watts. So the efficiency can be, in this case, the efficiency will be 100%. We can take the efficiency is 100%. So if I have the only series element, the efficiency will be less, which is equal to 50%. If I add the shunt element, what happens? The efficiency will increase to the 100%. So What is this function of shunt element? So it should supply the 10 amperes. You should also have the 10 amperes. So 10 plus 10, which is equal to 20 amperes. So that the condition will be satisfied, the efficiency will be improved. Now, so there is a series element and shunt element. Now let us replace these two elements as switches. Now let us replace these two elements as switches. Right? So which is the basic topology, which is basic deriving topology for the any converter, which is buck converter, boost converter, buck boost converter. So which is the basic topology. It has the two switches. It has the two switches. So what are all the switches? So we can derive. So these switches can be replaced. Later on, these switches can be replaced with the transistors and the diodes also. Now let us derive the buck converter topology. How the buck converter topology has derived, let us see. For example, now we have the two switches, like series switch and shunt switch. Two switches we should have in any topology to get the more efficiency, or to get the condition as satisfied as efficiency is 100%. Now we have the two switches, series switch and the shunt switch. Two switches we have. So in any additional elements should be added. So let us see. For example, if I add the inductance, what is the function of inductance? To eliminate the input current harmonics. As I said before, to eliminate the input current harmonics, to eliminate the input current harmonics, we should add the inductance. So to eliminate the output current harmonics, we should add the capacitor. So for example, so for this circuit, to get the buck converter for this circuit, we need to add the inductance and capacitance. So for that, we should know the fundamentals. So what are those fundamentals? So when you are adding the inductor to the circuit, it should not be in series with the switch. It should not be in series with the switch. So we should not connect the inductance in series with the switch. If I connect the inductance in series with the switch, what happens? So if I connect the inductance in series with the switch, so here L di by dt is the voltage across the inductance. Voltage across the inductance. So what happens? So if I interrupt the current suddenly, for example, initially it is having the 50 ampere something. Now suddenly I disrupted to the, so I opened the switch. What happens? The current will immediately, it becomes to zero. So then during that time, during the fraction of milliseconds, if I make the current equal to zero, so what happens? This di by dt is more, which causes high voltage across the inductance, and which will damage the inductance as well as whichever the devices are connected to the circuit. So we should not connect. The basic funda is we should not, in any circuit, we should not connect inductance in series with the switch. Inductance in series with the switch. So and the second point is capacitance we should not connect parallel to the switch. So for example, if I take the capacitance, I should not connect capacitance in parallel with the switch. So why? Because let us see. For example, the voltage across this one. So if I close the switch, what happens? The voltage across the capacitance will become zero during the fraction of milliseconds, because these are the power electronic switches, so which will operate in the high frequencies. So in a very less time, so the voltage variation is more, so which causes IC equal to C into dV by dt. The time is very less, and if I disrupt the voltage, so here what happens? Which causes high current through the switch. Which causes high current flowing to the switch. So which may damage the switch as well as whichever be the elements are there in the circuit. So it may damage that elements also. So that we should not connect the capacitance in parallel with the switch. So while deriving any circuit, we should consider these two fundamentals. What are those fundamentals? The switch should not connect. So the switch in series with the inductance, the switch should not connect in parallel with the capacitance. These two conditions should be satisfied. So now let us see. So So here, let us assume that it has the source here. Right? So now, let us assume that it has load here. Let the load will be the resistive load. Let us assume that load will be resistive load. Now, we have the source and we have the load and we have the basic topology, that is core topology. We should have the shunt switch and series switch. Two elements should be there in this circuit, which is equal to shunt, series element and the shunt element. Now, in this circuit, we should add the capacitance and inductance. So, where we should add the capacitance? At the load, obviously. Because, so the capacitance function is to eliminate the output voltage harmonics. So, capacitance should be added here. Capacitance should be added here. So, where should be the inductance should be added? Shall I add here? Shall I add here? So, in this point, if I add the inductance here, so here this condition is violated. That is, the inductance should not connect in series with the switch. So we cannot connect. We cannot connect. Now, so here inductance, can I connect here? So can I connect this point at this point? So we should not connect, because so the inductance in series with the switch will cause the high voltage across the switch. So we should not connect. So we can connect here. So the total circuit would be like this. So what is this circuit? Which is buck converter. Which is buck converter. Right? So the topology of the circuit is derived like this. If you know the fundamentals, you can easily derive the circuit. Let me call this as a L and C and load is R plus minus V0. So this is the circuit of the buck converter. This is the circuit of buck converter. Now, so if I want to derive for the boost converter, so what is the buck converter? In a buck converter, the output voltage is less than the input voltage, which is also called a step down converter. Now, if I want to derive for the boost converter, what I need to do? So, for example, if the source is this side, so the input voltage is greater than the output voltage. But if the source is this side, if you see from this side, if the source is connected here and the load is connected here, what is the circuit? Which is the boost converter. If the source is connected this side, I eliminate the resistance, I connected the source here. So I eliminate the DC source and I connected the resistance here. So what is the, let us draw the boost converter. So as I said before, so the boost converter is, so which if you seen from the load side, so if the load and source has reversed, it will be the boost converter. So how could we draw the boost converter? So if I connect the source here, so the starting element should be shunt element and then series element. So for example, if I want to draw the boost converter, so how could I draw the boost converter? So let us draw the boost converter here. So now I want to draw the boost converter. So boost converter. So let us draw the boost converter. So to draw the boost converter, so the switch should be, the source is here. Let us assume that the source is here. The source is here, and then, so we need to draw the shunt switch here, and then series switch, So now, so let us connect the load here. Now, so we can connect the capacitance here, because the main function of the capacitance is to eliminate the output voltage harmonics. Now, let us draw the inductance. Where we can draw the inductance here in this circuit. So, shall we draw here? So, we cannot draw in series with the switch. Here also we cannot draw. And we can draw here. At this point, we can draw the inductance. So, this is the circuit topology of boost converter. So, or else we can say like this. So, if the inductance on the load side, if the inductance on the load side, so we can call this as we can identify this as a buck converter. So if the inductance is connected in the source side, so we can identify this as a boost converter. So now let us see. So how we can draw the buck converter, how we can draw the boost converter, how we can draw the buck boost converter. So before that, let me classify what are all the different DC to DC converter we have. So based on the classification of DC to DC converter, let us see the classification of DC to DC converters. Of DC to DC converter. Classification of DC to DC converters. So what are the different types of DC to DC converter? So based on voltage level, let us consider based on voltage level. The first thing is based on voltage level. Based on voltage level. So it is classified into, the DC to DC converters are classified into step down or buck converter. Step down chopper, it can also called as chopper. So buck converter. Right? So and the second classification is step up or boost converter. Boost converter. So the third classification is, so we can classify it as a step up by step down or buck boost converter. We can call this as a buck boost converter. Buck boost converter. So what is buck converter? So in the buck converter, the output voltage is less than the input voltage. So we can call this as a buck converter. If the output voltage is less than the input voltage, we can call this as a buck converter. So what is the boost converter? If the output voltage is greater than the input voltage, we can call this as a boost converter. So if the output voltage we can increase or decrease, so it can operate in the step up or step down based on the duty cycle. So we can call this as a buck boost converter. So and then based on the commutation technique, so we can classify it into voltage commutated chopper, and the current commutated chopper. So the next classification is based on quadrant of operation. So the DC to DC converters are classified into type A chopper, so type B chopper, so type C chopper, type D chopper, and type E chopper. For example, so if I take the current on x-axis, I0, output current on x-axis, so which is equal to minus I0. So voltage on y-axis, V0 and minus V0. So if it is type A chopper, will operate in the first quadrant. That is V0 and I0 both are positive. If V0 and I0 both are positive, so we can call this as a type A chopper and it is operate in the first quadrant. So if the type B chopper, that is V0 is positive and I0 is negative, so which is called as, it is operating in the second quadrant. So and then type C chopper will operate in the first and second quadrant. In both the quadrants it will operate. So type D chopper will operate in the quadrants of first quadrant and fourth quadrant. So the type E chopper will operate in all the quadrants, like V0, I0 positive, V0 positive and I0 is negative. So both the voltage and current is negative and the current is positive, voltage is negative. In all quadrants it can operate. So we can call this as a type E chopper. So based on the quadrant operation, it is classified into this type of classification. So like that, DC to DC converters are classified. So now let us see how the buck converter, boost converter and buck boost converter can be drawn. So as we seen before, if the inductance in the load side, it is identified as a buck converter. If the inductance on the source side, so it is identified as a boost converter. If the inductance in between both the source and load, it is identified as a buck boost converter. So now let us draw the three converters. So let me draw the buck converter. Let me draw the buck converter. So what is buck converter? So if the inductance is connected load side, so I need to connect the inductance on the load side. So the switch should be here and the shunt switch should be here and inductance is connected here. So capacitance is connected here and the load is connected here. So VDC, let us assume this switch is S1 and this one is S2, inductance, capacitance and the load. So which is buck converter. So how can we draw the boost converter? So if I want to draw the boost converter, so let me draw the boost converter here. Let me draw the boost converter here. So what is the boost converter principle? If the inductance is connected in the source side, so we can call this as a boost converter. So if the inductance is connected in the source side and the shunt switch, series switch, and the capacitance, load. So we can call this as a boost converter. VDC, L. So switch 1 and switch 2, capacitance and the resistance plus minus V0. So if the inductance is connected on the load side, so it is a buck converter, it is identified as a buck converter. If the inductance is connected on the source side, it is identified as a boost converter. For example, what is the buck boost converter? So the buck boost converter is if the inductance is in between the source and load, so we can call this as, we can identify as a buck boost converter. Let us see. So how the buck boost converter? The buck boost converter So if the inductance is connected in between both the source and load. So source is here, let us assume source is here. The switch 1 is connected here. Switch 2 is connected here. So capacitance and the resistance. So if the inductance is connected, switch 1 and switch 2 here, so it will be the buck boost converter. So in this buck boost converter analysis, we will place the minus sign here and plus sign here to get if you derive the output voltage, to get the output voltage is positive. So we will keep the sign like this and I0 will be like this, right? So this is switch 1 and switch 2. So if the inductance is connected in between the source and load, so it is a buck boost converter. Now let us see. So we can call this buck converter. We can also define the buck converter like this. So what is the buck converter? Inductor is connected in the load side. So we can make it as so it is a voltage source VDC. Let me call this as the V. And the switch is here. So how the switch is here? The switch will be here. If I replace with the single pole double throw switch, it will be like this. And the current source is like. So because inductance is connected in the load side, so the inductance doesn't accept the sudden change in the current, so it can make it as a constant current source. So which buck converter is also called as VI converter. Buck converter is also called as VI converter. So how the boost converter will be? So I can replace this switch as this as a common point, and so we can replace like this. So position 1 will be like this and the position 2 will be like this, right? If we call this as a common point. So if I connect to the position 1, the switch 1 will be on condition. If I connect to the position 2, the switch 2 will be on condition. So for example, so where the inductance has connected, the inductance is connected on the source side. The inductance is connected on the source side. So if the inductance is connected on the source side, so I can replace this inductance as a current source, right? Current source. And if I take the inductance is a common point here, so common point O, the switch 1, let me represent like switch 1 like this. It is a 2-position switch. So here, switch 2 will be like this. And then, so here I can represent with the voltage source. So what is this converter? So this converter is IV converter. IV converter. So the boost converter is also called as IV converter. Now, so let us take the buck boost converter. So if you take the buck boost converter, so where the inductance has connected, so the inductance is connected in between the source and the load. So the current source will be like this. The current source will be like this. And we have the voltage source V1. And let us assume that the output is also having the voltage source. The output is also having the voltage source. So we can take it as a switch like this. Position 1 and position 2. And one more voltage source, which is equal to voltage source V2. So how we can call this converter? So VIV converter. VIV converter. VIV converter. So now let us conclude the session. So let us conclude up to here. So here, so the buck converter, based on the converter topology, based on the fundamentals, we have drawn the boost converter, buck converter and buck boost converter. So if the inductance on the load side, so we are making it as we are identifying it as a buck converter. If the inductance on the source side, we are identifying this as a boost converter. If the inductance is placed in between the both source and load, we are identifying it as a buck boost converter. So the buck converter is called as VI converter. So boost converter is called as IV converter, and the buck boost converter is called as VIV converter. VIV converter. Now let us solve some questions on this. So now let it be the first question. So what is this question? Let us see. So in this question, it is the power electronic converter has given. So which converter we need to identify? So by observing this, we can find that so it is a buck converter or step down converter, step down choker. So why? Because the inductance is placed at the load side. If the inductance is placed on the load side, so we can call this as a step down chopper or buck converter. Step down chopper or buck converter. So let us solve the next question. So the device used for the switching mode power supply. So what is switch mode power supply? Let me explain you. Let me explain you in a brief manner. So the converters or the DC to DC converters are also classified based on isolation property. So which is called as non-isolated converter. So what we have derived, like buck converter, boost converter, buck boost converter, SEPIC converter, Kirk converter, like different converters are there, and these converters are non-isolated converter. So one more converters also there, so which are called as isolated converters. So isolated converters in the sense the input and output are isolated by the transformer. So this isolation transformer, to reduce the isolation transformer size, they will operate the switches at high frequency. So generally, the switches which are operating at high frequency so are the MOSFET, so which are called as the switch mode power supplies. We will use the, in switch mode power supplies, we will use the isolated DC to DC converter. So in the isolated DC to DC converters, we will operate the switches at high frequency to reduce the size of isolation transformer. So the MOSFET will operate at the high frequency. We will use the MOSFETs. The device used for the switching, in case of switched mode power supply, will be the MOSFET. Now, let us see the next question. So, a buck regulator, which is nothing but buck converter, has given the voltage of 12 volts. The input voltage is given as 12 volts. The input voltage is given as 12 volts. And output voltage is 5 volts. V0 is 5 volts. And then what is the duty cycle? Very simple question. What is the duty cycle? So, it was asked in the previous question paper. So, previous question paper of CSC, I think in civil services. So, duty cycle equal to, so we know that output voltage equal to input voltage into duty cycle. So, duty cycle equal to V0 by Vs. So, what is V0? So, it is equal to 5 and I0 Vs equal to 12. So, the answer is 5 by 12. The answer is 5 by 12. So, now let us solve the next question. Let us solve the next question. So, you can answer this question. What is this? Which of the following circuit represents an equivalent circuit for the buck-boost converter? First, what we have to remember, in case of buck-boost converter, the inductance is placed in between the source and load. The inductance is placed in between the source and load. So, here, and it is a VIV converter. So, the current source in between the two voltage sources. So, here in this circuit, if you observe, the current source is in between the source and load here, and this circuit is input is voltage source and output is also voltage source. So, VIV converter. So, option C is the right answer. Option C is the right answer. So, now let us see the next question. So, it is a step down chopper. It is a step down chopper. And it is asked for the discontinuous load current. So, we haven't covered this topic. So, after covering this topic, we'll answer this question also. Now, the circuit shown in the figure. So, what is this circuit? What is this circuit? Let us see what is this circuit. So, what is this circuit? So, if you observe the circuit, the inductance is here and the two switches are here. Two switches are here. The switch 1 is represented with S. The diode will also act as a switch in case of the power electronics. So, two switches are there and the inductance is placed in between the two switches. So, what is this topology? What is this topology? This topology will be the buck-boost converter. Buck-boost converter. So, which is asked in the ESC 2007. So, now let us see the next one. Let us see the next one. So, which is step up DC to DC converter. We haven't covered this topic. So, let us solve the next time. So, this is asked in the ESC, CSE, Civil Service Examination. So, let us see. So, here, so the chopper circuit is operating in the TRC principles, time ratio control principles. So, frequency is given as 2 kHz. Frequency is given as 2 kHz. Frequency is given at 2 kHz. Supply voltage is given as 220 volts. Supply voltage is given as 220 volts DC. So, which is equal to Vs equal to supply voltage. Load voltage is given as 170 volts. 170 volts is the load voltage. So, the conduction and the blocking period we need. So, that is T on and T they want. T on and blocking period. So, that is T of them. We need to find the on time of the switch and off time of the switch. So, how can we find the on time and off time of the switch? So, first let us find the duty cycle. So, here what is this circuit, which is a buck converter or boost converter? So, the input voltage is more and output voltage is less. So, it is V0 is less than Vs. So, which is a buck converter. So, what is the output voltage expression for the buck converter? V0 equal to Vs into duty cycle. So, from this you can find the duty cycle. So, what is the duty cycle here? V naught by Vs. V naught by Vs. That is 170 divided by 220. 17 by 22. I think calculator is not needed. Let us see. 17 by 22. So we got the duty cycle. What is the time period they have given? 2 kilohertz. Frequency is given as 2 kilohertz. From that total time we can calculate. So which is equal to 1 by f. Right? So 1 by f equal to 1 by 2 kilohertz. 1 by 2 kilohertz. So which is equal to 0.5 milliseconds. 0.5 milliseconds. Now, so I need to find the T on. So what is the T on? So T on equal to, so duty cycle equal to T on by T. So what is the T on? So which is equal to 17 by 22 duty cycle into total time. 0.5 milliseconds. 0.5 milliseconds. So if I find that, I will get the T on as 0.386 milliseconds. 0.386 milliseconds. So now we got the T on. So which is the time ratio control. So which is nothing but the total time is constant. The total time will not change. T on can be changed. Only T on will be changed. The total time is constant. So the T on will be T on and T off will be changed. So T on plus T is always constant in case of TRC principle. So what is TRC principle? The time ratio control. So that in the time ratio control, the T on will vary, T off also will vary, but the total time will always constant. So the total time is 0.5 milliseconds, on time is 0.38 milliseconds, 386 milliseconds. What is the off time? So the off time equal to total time minus on. So how can we find the off time? So which is equal to total time minus on time. So 0.5 milliseconds minus 0.386, which is equal to 0.114 milliseconds. So option D is the right option. Right? So now let us solve the next question. So which is also asked in the UPSC civil service examination. A DC chopper has a resistive load of 10 ohms. So it has a resistive load of 10 ohms. R is given as 10 ohms. Resistive load of 10 ohms. And then, so the input voltage is 220 volts. Input voltage is given as 220 volts. When the chopper switch on, the voltage drop is 2 volts. Voltage drop is equal to 2 volts, which is equal to voltage across the switch equal to 2 volts. Voltage drop across the switch is given as 2 volts. And the chopping frequency is 1 kilohertz. So frequency is given as 1 kilohertz. And then duty cycle is given as 0.5. So let me explain clearly. If you are new to the topic, let me explain you clearly. So what they have given? The chopper is given. Simple chopper, the average output voltage we need to find. So whether it is buck converter or the boost converter or the buck boost chopper, how we can find? If you see the options, all the options are less than the input voltage. So it is obviously buck converter. How the buck converter would be? The simplest buck converter is, in case of resistive load, 2 switches are not needed. So we can take 1 switch. So which is a buck converter, which is a simple buck converter. Right? So how much it was given? It is given as 220 volts. And voltage across switch is given as 2 volts. The output voltage V0 we need to find. And the resistance also given, I think, which is equal to 10 ohms. So how could we find? Let us see. So let me draw the output voltage waveform. If you know the concept, you can solve it in the less than a minute, but let me explain you clearly. So if I want to draw the output voltage, when switch is in on condition, let us assume that up to T on, that is T on by T is given as 0.5 T. So half of the time, 0.5 T, which is given as, how much it was? So the output voltage, the switch is in on condition. When switch is in on condition, so the voltage drop across the switch is given as 2 volts. That is, across the chopper, the voltage drop equal 2 volts. So the output voltage is 220 minus 2. That is 218, right? 218 volts. 218 volts. Up to T on, it is 218 volts. And the remaining period, it will 0. So now we need to find the output voltage. So which is equal to 218 into 0.5T. 0.5T is the T on. 0.5T is the T on divided by total time. So 218 into 0.5, which is equal to 109. 109. Right? So if the voltage across the switch, if you consider the voltage across the switch, because the switch has an internal resistance, definitely there is a voltage drop across the switch, but in all cases we are to make the analysis, we are making it as a 0. The voltage drop across the switch equal to 0. We are considering the ideal switch for analysis, but in this case, the non-ideality is considered. So which is nothing but the voltage drop across the switch, that is, they are considered the internal resistance of the switch also. So answer is 109 volts. So that's all for today. So we discussed about the very fundamentals of the DC to DC converter. So in the next session, let me discuss about how these converters are operating in the continuous conduction mode, how these two switches can be replaced by the power electronic switches. Let us find the different parameters in the DC to DC converter, like buck converter, boost converter, and buck boost converter. Let us solve all the problems that are given in the different competitive examinations. Right? So let us meet in the next session. So thank you so much. Thanks for attending the session.